Hello everyone, welcome back to Diksha Karnataka YouTube channel, and in the Sankalp KCET 2026 I am going to discuss about Ampere's law, galvanometer to ammeter in the chapter moving charges and magnetism. Today is the second part of this chapter, second and last part. If you have missed the first part, then you have to go to our channel, subscribe to our channel, and then go to the playlist section where you will find all the chapters that I have completed in Sankalp KCET 2026 batch. Now, if you have not yet subscribed, definitely I request you to subscribe to our channel. Secondly, if you have not yet joined our WhatsApp channel, the link of the WhatsApp channel is given in the description of this video. So don't forget to join our WhatsApp channel so that you don't miss out on any update that we are doing in our channel. Now let us discuss the chapter summary. So Lorentz force, motion of a charge in magnetic field, magnetic force on a current carrying conductor, magnetic field due to a current element, Biot-Savart's law, application, magnetic field due to a straight conductor, circular current loop, magnetic field versus electric field, mu naught and epsilon naught. Everything of these are discussed in my part 1 video. Today I am going to discuss Ampere's law, application for straight conductor, solenoid, force between two parallel currents, torque on a rectangular current loop, circular current loop as a magnetic dipole, galvanometer, ammeter and voltmeter. So these are everything that we are going to discuss in today's lecture. So let's start with Ampere's circuital law. Very simple, easy law. It states that the line integral of the magnetic field around any closed loop equals to mu naught times the total current passing through the surface. So basically, what is the meaning of that? So it is the mathematical statement. So if you see the diagram, suppose we have a loop, it called Amperian loop. Okay, Amperian loop is same as Gaussian surface. Okay, Gaussian surface is basically where you are considering a surface, a two-dimensional surface. It can be a spherical surface, it can be a cylindrical surface, right? In case of Ampere's law, it is a two-dimensional loop. Okay, Amperian loop, it can be a circle. Okay, it can be a circle, it can be a rectangle, any odd shaped loop as well. It has to be a closed loop. If it is open, then Ampere's law is not applicable. If it is closed, you can apply Ampere's law. Okay, and what does it states? Similar to that of Gauss law, it states that the line integral of magnetic field on the point on this line, point on this loop. Okay, any point, suppose at this point magnetic field is B. If you take a small element over here and make a dot product of B and dl, okay, and if you what will be the value of B dot dl? That will be the mu naught times the current enclosed. Current enclosed means it has to pass through a current carrying conductor. For example, if suppose this pen carries some current. Okay, this pen is carrying some current, suppose in this direction. Now if you construct an Amperian loop around this current carrying wire, okay, then according to Ampere's circuital law, the magnetic field on each and every point on the surface of this loop can be calculated using this formula: integral B dot dl equals to mu naught I. I is the current enclosed in this case. It is similar to that of Gauss's law. In Gauss's law, it was electric field and it was charge enclosed, right? So charge enclosed instead of charge enclosed, it is current enclosed, and secondly it is B dot dl and integral close integral. Similar to that of Gauss's law, if the surface is if the Amperian loop is symmetrical or partially symmetrical, it is easier for us to calculate this integration, right? For example, the circle is the most common case where circle is the most symmetrical two-dimensional object. So you can use circular Amperian loop as much as possible. In certain cases, we can use a rectangular loop as well. For example, in case of solenoid, we use rectangular loop. Okay, for normal current carrying wire conductors we use circular loop. So here you can see that some of the lines are passing through this surface, okay, and you can apply the Ampere circuital law to calculate this expression. Similar to that of Gauss's law, it is not something completely different. Okay, in fact later on you might find they are related, okay, through some another law, Maxwell's law. You will see that Maxwell gave 4 laws, and from there he established electromagnetic theory. So it is part of Maxwell's law, and Ampere's law is partially incomplete. That also there is a Maxwell who completed that, and it was called Ampere's Maxwell's law. But for now, for this chapter, this information is sufficient, and maybe in some cases you will see some problems coming directly from this law. But main part is so let's see one question. Two identical current carrying coaxial loops carry current I in opposite sense. A simple Amperian loop passes through both of them once, calling this loop as C. Okay, then what will be the answer? So first let us understand this question. We have 2 straight wires, okay, they are carrying current and they are coaxial. Coaxial means they are not simply like this. Suppose this is one wire, okay, and second one is passing just through center of that. Okay, so these are just like pipes, okay, water pipes, similar to that, metallic pipes. Okay, a current say pass through this, say I. Okay, it says that carry current I in an opposite sense. What is the meaning of opposite sense? So if this outside one carries a current in the upward direction, then the inside one will carry a current in the downward direction. Okay, now if you construct an Amperian loop, simple Amperian loop which passes through both of them only once means once through the outer one, once through the inner one, like this. There is no complicated Amperian loop, it's simple Amperian loop. Now what will be the formula for this? That you have to find. The value of B dot dl is equal to plus minus mu naught I. Let's see, the value of B dot dl is independent of sense of C. There may be a point on C where B and dl are perpendicular. B vanishes everywhere on C. So let's see. So what is the meaning of the last statement? Last statement is nothing but B dot dl equals to 0. Now if you see that B dot dl is dependent on the current I. Now what is the current I in this case? So one current going upward, that means plus I. Okay, what is the current enclosed over here? Current enclosed in this case, okay, suppose this one is positive, then this one will be negative. So I minus I, that is 0. So total current enclosed by this Amperian loop is 0. So does not matter the C, wherever you go, okay, B will be 0, because current are in the opposite direction. So B vanishes everywhere on C. Why? Because B dot dl equals to mu naught I, so it is 0. DL cannot be 0, so only thing that can be 0 is B. Okay, so B will be 0 on this line. Magnetic field due to a straight conductor. So I told you that I will do this small derivation using Ampere's law, which is much easier to do than using Biot-Savart's law. Okay, so let us consider one very long wire carrying current I. Okay, and we want to find a magnetic field at some point P. We want to find magnetic field at some point P. Now for that, what we have to do? We have to construct an Amperian loop. Amperian loop is not there from the beginning. We constructed it based on the point P, so that the radius is same, right? So radius of this circle is same, and based on our requirement we have constructed this Amperian loop, circular Amperian loop. Right, so always similar to that of Gauss's law, we will always try to construct symmetrical lines. Right now what is the current enclosed over here? Current enclosed is given I. So let us apply Ampere's law. B dot dl equals to mu naught I. That is simple law. Now what is dl over here? Dl is this, right? So dl will be, you can take in this direction or whatever direction, that does not matter. In this case, suppose we are taking in particular direction, so dl will be in this direction. What will be the direction of the magnetic field? Okay, magnetic field will be perpendicular to that of the dl direction. So magnetic field will be dl, suppose in this direction, magnetic field will be another perpendicular direction. Okay, so B and sorry, not perpendicular direction, oh my god. So dl will be also let me erase this. So dl, so this is the direction of current, so dl is in this direction. So Amperean loop, because of it's a circle, B will also be in the same direction. B will also be in the same direction. Okay, so B dot dl, that means it is basically B into dl. Why? B dot dl means B dl cos theta. Now cos 0 is 1, cos 0 1 means we can write simply B into dl, right? So in this case, because B and dl are in the same direction, angle is 0, angle 0 means cos theta, A dot B is AB cos theta, so theta 0 means cos theta is 1, so we can simply write B dl. Also this is a symmetrical surface, right? Symmetrical line. The line is symmetrical. So line symmetrical means whatever is the magnitude of B at this point, whatever is the magnitude of B at this point, the magnitude of B will be same at each and every point, because it is symmetrical. Okay, it depends on distance. Now distance is same for each and every point, it's a circle. So distance is same for each and every point, direction will be different, yes, but magnitude wise it will be same. So we can take this magnitude of B out of the integration and we can write this as dl mu naught I. Now what is this closed integral dl? What is the meaning of integration dl? Integration dl means we have one small portion of this circle. We have one small portion and we are saying this is dl. Now what is the meaning of this? This sign represents closed integral. What is the meaning of closed integral? Closed integral means you take all small dls, you take all small dls, and integration means basically addition. I already told you integration means addition, and your starting point and your ending point should be same. So if you start from this point and if you take small portions and if you add them up to this point, so what is the meaning of that? That means you are basically trying to calculate the perimeter of a circle in this case, right? Perimeter of the line. So perimeter means, what is the perimeter of a circle? Perimeter of a circle is nothing but 2 pi r, right? 2 pi r is the perimeter of a circle. So from here we get mu naught I, or on simplifying you can get the magnetic field in this case is given by mu naught by 2 pi I by r. It is not r square, by the way, sorry. It will be mu naught by r, right? So this is the formula for magnetic field due to a straight wire. Magnetic field due to a straight wire is mu naught by 2 pi I by r. Now solenoid. What is a solenoid? Solenoid is basically, if you take, suppose you take a small cylindrical object, okay, like the handle of a bat, simply handle of a bat, or any simple rod, pipe. So if you take that water pipe and if you wind some metallic insulated wire, okay, not normal wire but insulated wire, if you take it and if you wind it on that cylindrical object like bat handle or the pipe, if you wind it, then this structure is called solenoid. okay, and if you connect it into a battery, DC battery, okay, then it will behave as a magnet. Then it will behave as a magnet. So you are taking a cylinder and then you are winding some wires around it, insulated wire, okay, and if you wind them and then if you connect it to a battery, then this structure is called solenoid. It will behave as a magnet. It will show some magnetic property. Just like a magnet, it can attract magnetic materials like iron. Also it will have a magnetic field on its own. The magnet means it has to have some magnetic field. So the magnetic field expression is given by mu naught Ni. Mu naught means inside portion is hollow. Okay, hollow means there is nothing inside, it is vacuum. But if you add any other material inside, then this B with that material, say Bm, will be mu naught, not mu naught, mu Ni. Okay, mu is the permeability of the core. Okay, you can use an iron, you can use any metal, okay, generally we use metal. Magnetic material is good, for example iron, nickel, cobalt, you can use any one of them inside, right? What is this N signifies? This N signifies number of turns per unit length. So total number of turns does not matter. Okay, if you can wind up a very large number of turns in a small region, in that case small n will be very high. Higher small n means higher magnetic field. So if you want to generate significant magnetic field, the number of turns in that area should be very, very high. Okay, for a small length, if you can increase the number of turns, you will get a very high magnetic field. I, obviously I represents current. Okay, I represents current that is passing through the circuit, right? So from this you can calculate the magnetic field due to a solenoid. Based on this formula, a lot of questions have come in the past and it will come in the future as well. So let's see one of such question. A solenoid of length 50 centimeter having 100 turns carries a current 2.5 ampere. The magnetic field at one end of the solenoid is. Now the magnetic field expression that we have seen is for the central portion. Here this expression is for the central portion. This is the magnetic field. Okay, not for the end. This is not true for end. Okay, so for end what you have to do, you have to remember that whatever is the magnetic field at the center, at the end it will be B by 2. At any end it will be B by 2. So if you can calculate the magnetic field at the center, near the end it will basically becomes half. It slowly decreases as you are moving away from the center, but most part of the central region we can assume it is constant. But when they ask you to find the magnetic field at the end, then you have to calculate that magnetic field and then divide it by 2. That will give you the magnetic field at the end. Now how to do that? First of all, length is given, total number of turns is given. This is not n, by the way. Having 100 turns means the total number of turns, right? So length of the solenoid is 50 centimeter. 50 centimeter means what? 50 into 10 to the power of minus 2 meter, right? Now total number of turns we generally represent using capital N. Okay, so this is 100. So what is the number of turns per unit length? Number of turns per unit length is total number of turns divided by the length of the wire, and it will always be in SI unit. So 100 divided by 50 into 10 to the power of minus 2. So you will get 2, so it will be 200. 200 turns per meter. 200 turns per meter. 10 to the power of minus 2 will go up and it will become 10 to the power of 2. That will be that will give you 100. So 100 and this 100 get cancelled and we got 2 over here, 52 is 100. So 2 into 100 is 200. So this is the number of turns per unit length, right? Now we have calculated n, I is already given, mu value we know, okay, we will just put that. So B is given by, B at center is given by mu naught Ni. Okay, now what is the value of mu naught? Mu naught by 4 pi is 10 to the power of minus 7. So mu naught will be 4 pi into 10 to the power of minus 7. Put that value over here, you will get 4 pi into 10 to the power of minus 7. N is 200 and current is 2.5 ampere. Okay, just simply multiply it and simplify. So it will be 4 into 2.5 is 10. 4 into 2.5 is 10. So it will be 2000 pi into 10 to the power of minus 7. Right? 200 into 10 is 2000. Now let's reduce the 10 to the power value. So we get 2 pi 10 to the power of minus 4. 2 pi into 10 to the power of minus 4. 2 pi means pi is 3.14. Pi is 3.14 approximately. So it will be 2 pi will be 6.28 into 10 to the power of minus 4 Tesla. So 6.28 into 10 to the power of minus 4 Tesla. This is total magnetic field. The magnetic field at end, don't make this mistake. Don't mark option D as correct. Okay, magnetic field at any one of the ends will be half of the center value. Half of the center value. So it will be 3.14 into 10 to the power of minus 4 Tesla. Okay, so correct answer is option B. Okay, at end they ask you one end, okay, not at the center. If they ask you about center, then this would have been the correct answer, but because they have asked at one end, that means it will be BC by 2, center by 2. Now force between two parallel currents. We have two current carrying wires, okay, parallel as well as anti-parallel. Okay, parallel does not always means only in the same direction. Even this can be considered to be a parallel, but they are going in the opposite direction. So this is called parallel and this is called anti-parallel. So what will be the force between two parallel current carrying wires? The expression for force is given by mu naught N Ia Ib L into D. So suppose the current passing through this wire is given by Ia. Current passing through this is IB, the distance between the wires is D, and for time being I am considering a length L. Okay, they are not infinite wire, they have some length L, so the length is L. So this is the expression for force between these two wires. Why two? First of all, let us understand why two current carrying wires will repel each other or attract each other or even apply some force on each other. Why it is so? So first of all, a current carrying wire will produce a magnetic field, right? We have learned in the last class that formula was BIL sin theta, right? BIL sin theta was the formula for magnetic field due to a current carrying wire. Okay, magnetic field due to a current carrying wire we did today's class only, also in the last class, that was mu naught I by 2 pi r, right? Mu naught I by 2 pi r, that is the magnetic field due to any current carrying wire. Now if you place another current carrying wire in the presence of the magnetic field due to the first wire, then because of the magnetic field of the second wire, the first wire will experience the force BIL sin theta. Okay, so current carrying wire not only produces its own magnetic field, okay, it also affected by any external magnetic field as well. clear the doubt in your mind. So current carrying wire produces its own magnetic field. It also gets affected by external magnetic field, right? So this wire is producing a magnetic field. You can consider the second wire is getting affected by its magnetic field. Similarly, this wire is producing its own magnetic field, and the second wire is getting affected by the first magnetic field. So basically two friends, okay, so one is writing the exam, another one is trying to copy from it. Again, whatever he is writing, the first student is also trying to copy from the second student, right? So both of you copy from each other, but you don't know the answer, so you know what you will write in the exam hall, right? So that is what is happening between these two wires. So one is producing magnetic field, the second one is getting affected. The second one is producing magnetic field, the first one is getting affected, so and so. Okay, so also according to Newton's third law, if this wire applies a force F12 on this, and this wire is applying a force F21 on this, according to Newton's third law, there is no other external force is present. That means these two forces must be equal and opposite, and F12 will be minus F21. Magnitude will be same. Now, what is the definition of ampere? From this expression you can define ampere. The ampere is the value of that steady current which, when maintained in each of these two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce a force on each other equal to 2 into 10 to the power of minus 7 newtons per meter of the length. So if you take two wires, okay, two wires, the distance between them is 1 meter, the length is 1 meter, and if you apply 1 ampere current through both of these two wires, okay, then they will apply a force of 2 into 10 to the power of minus 7 Newton. Okay, which is a very small force, 2 into 10 to the power of minus 7 Newton. This much force will be applied between these two wires. So that is how the ampere is defined. So far ampere's direct definition was not given. It is 1 coulomb per 1 second, which is not super conclusive, but this in terms of force that we can measure is very, very important to define. Later on there are other definition of ampere as well, but this is one of the very first definition of ampere. Okay, also you have to remember that if the current is being flown in the same direction, parallel currents, they actually attract each other. If the current is being flown in the same direction, they attract each other. Okay, parallel currents attract, and anti-parallel current, that is if the current is flowing in the opposite direction, they repel each other. Okay, so parallel currents attract, anti-parallel currents repel. Now let's see one question. Two parallel wires in free space are 10 centimeter apart and each carries a current of 10 ampere in the same direction. The force exerted by one wire on the other per unit length. So per unit length means, what is the meaning of per unit length? Per unit length means you have to take this length L as 1. Okay, as simple as that, mu naught Ni Ia Ib. But what is this N in case of one single wire? If we have multiple wires, okay, then this N comes into picture. Otherwise this N also does not have too much effect. So what formula we will use? We will use the simple formula F equals to mu naught I1 I2 by D. Now if you see the question, two parallel wires, free space, 10 centimeter apart, so distance is 10 centimeter, and each carries 10 ampere current. So both the currents are same, right? So what is the value of mu naught? Mu naught is 4 pi into 10 to the power of minus 7. Okay, both are 10 ampere. And the distance is 10 centimeters, so 10 into 10 to the power of there was one small correction here. Here will be 2 pi d. Okay, there will be a 2 pi in the division of this formula. Okay, So here also we have to apply this 2 pi, okay, and 2 pi means pi cancels, we get 2 over here, and 10 to the power of minus 7, minus 2, minus 5, minus 4. So 2 into 10 to the power of minus 4 Tesla, or sorry, Newton. 2 into 10 to the power of minus 4 Newton per meter. Per meter is coming because we are trying to find the force per unit length. So that is why Newton per meter is coming. So now what is the direction, attractive or repulsive? So current of 10 ampere in the same direction. So same direction means it must be attractive. So 2 into 10 to the power of minus 4 in the attractive region. If there are carrying current in the opposite direction, then it will be 2 into 10 to the power of minus 4 repulsive. Okay, so those who are saying, sir, there is a error in the formula, I have corrected it. Okay, sorry for my mistake, I have corrected this formula. Now let's continue with our discussion. Torque on a rectangular current loop. Now there is a unique situation. We have a loop, current carrying loop. Okay, now we know that current carrying wire produces its magnetic field and they apply force on each other. In case it is kept in a external magnetic field, there will also be a force. Now if you keep two fixed magnet, say north pole and south pole, there will be a magnetic field from north to south. We will learn more about this in our next chapter, but for now you have to understand that there will be a magnetic field from north to south of the magnet. Okay, we have kept one north pole over here, another south pole over here. Now magnetic monopole is not possible, so you can consider this to be an U-shaped magnet. There are different ways to achieve this, but for now just simply understand that we have a north pole over here and a south pole over here from a larger magnet. That is the easiest way to remember. Now, so there is a magnetic field acting on this direction. Some current is passing in this direction, same current is passing in the opposite direction. A loop means current is entering, suppose current is entering from this. Okay, so it is passing here and it is exiting from here. So both arm of the loop carrying current in the opposite direction. Okay, so because of this magnetic field, one way there will be a force in the upward direction, and the opposite way the current there will be a force in the reverse direction. So one way it is trying to go up, and another way it is trying to go down. So what will happen? So two equal and opposite forces acting on an object but at a different location, it will create a torque. Torque means the thing will try to rotate. This is called motor motion. Okay, this is the basic fundamental principle of an electric motor. Okay, so this will try to rotate, and based on this principle our fans and many other electric motors, they basically work on this same principle. Okay, the torque acting on this system is calculated using this formula. Tau is equal to IA into B. I is the current, A is the area of the loop, A is the area of the loop. Okay, so from there you can calculate the torque acting on this current carrying loop. So A is the area and B is the magnetic field due to this external system. Magnetic field due to this external system is the value of B. Vectorially it can be written as tau equals to I A cross B. A is the area vector, B is the magnetic field vector. Maximum value is when A and B are in perpendicular direction, that is the maximum value, that is given by this. For any other intermediate position it will be IAB sin theta. Okay, the magnetic moment of a single loop is defined as M equals to I into A. So this is the definition of magnetic moment. So if you are considering a loop, okay, the loop will also produce its own magnetic field, right? So that is so if someone is producing a magnetic field, then it has to have some magnetic dipole moment. Okay, electric dipole moment similar to that of magnetic dipole moment. Okay, electric dipole moment plus and minus opposite. Similarly, a current carrying loop can be considered to be a magnetic dipole moment because they have opposite current. So one way, if one side if you consider north pole, the other side will automatically be south pole, and there will be a repulsion and attraction will happen, right? So that's why it is called a magnetic dipole. Okay, for n number of turns. Now if you consider this was a only single loop, now if you have n number of such loop, if you have n number of such loop, 1 2 3 4 like that, okay, so what will happen in that case? If you consider n number of loops, then the same magnetic moment will be NIA, National Investigative Agency. Okay, so those who takes care of India's internal security, etc., right? So it will be NIA. Thus tau equals to, the normal formula for tau becomes m cross b. Okay, it becomes m cross b. Check this question. A circular current loop of magnetic moment m is an arbitrary orientation in an external uniform magnetic field. The work done to rotate the loop by 30 degree about an axis perpendicular to its plane. Now work done formula I have not done, but normally the work done formula depends on simply this formula. The work done formula is mb cos theta 1 minus cos theta 2. Okay, so this is the normal formula for work done, but it says that the loop is in some arbitrary position. Loop, consider circular loop, it has some arbitrary position, and if you read the question carefully, arbitrary orientation in an external uniform magnetic field, the work done to rotate the loop 30 degree about an axis perpendicular to its plane. So it is about an axis which is perpendicular to its plane. So if you rotate the loop, okay, if you rotate this loop perpendicular to its plane by some angle 30 degree, okay, the direction, this is the vector A, this is the area vector A, this is also the direction of the magnetic moment vector m. Okay, I into A. So even if you rotate this loop, the direction of m and A will remain the same. Okay, so direction of m and A will remains the same. Only angle which determines this work done is the angle between the magnetic moment vector and the magnetic field vector. Now even if you rotate this loop in this direction perpendicular to this plane, okay, this theta will remain unchanged. So theta 1 and theta 2 value will be same. So theta 1 will be equals to theta 2. Why? Because this is angle theta, not this one. In this question they told you that it is rotated with an axis perpendicular to the plane of the loop. So perpendicular to the plane of the loop means the loop is being rotated in this direction, but the angle theta remains constant. So work done will be mb cos theta minus cos theta, that is 0. So work done will be 0 in this case. So work done will be 0 in this particular case. Okay, and this is the expression for work done, similar to that of a dipole. In case of dipole, if you remember, it is PE sin cos theta 1 minus cos theta 2. Similar over here, instead of PE it is m into b. Okay, now this obviously we have done in our last class, right? The magnetic field due to a circular current carrying loop, right? Now this expression has a special significance. I discussed it briefly in our last class also, that this is basically same as that of the electric field due to a dipole, right? Electric field due to a dipole, which is 1 by 4 pi epsilon naught 2p by electric field on the axis of a dipole, 2p by r cube, right? So similarly here also this is the expression for a magnetic dipole. Now what is a magnetic dipole? Magnetic dipole means basically a magnet. Okay, so circular loop can be used as a magnetic dipole or can be used as a magnet. Basically they behave as a magnet. Okay, so this is the proof. this is the proof that this is a magnet. Okay, I into A is the magnetic moment, and this expression is very similar to that. So from this comparison we can say that magnetic circular current carrying loops are acting as a magnetic dipole. Now how to find the direction? So direction is very important. To find the direction, suppose you are looking from the top of the circular loop. If you are looking from the top and if you see that current is passing in this direction, then it will be south pole. Okay, clockwise direction south pole, anti-clockwise direction is basically north pole. Okay, so anti-clockwise direction is north pole. Okay, so this is a way to remember that how can you find the direction of poles in particular case. So if you are looking from the top of the loop, okay, and if you find that the current is passing in a particular direction, based on the direction of the loop you can find, okay, this is in this direction, that means this is a south pole, whereas this is a N, right? So N means this is how you can find the direction. Okay, this is how you can find the pole of the circular current carrying loop. Now if you multiply multiple number of turns, so if you increase number of turns, then there will be a N multiplied over here, and M will automatically will have that small number of N, and that will increase the strength of the magnet. Okay, now moving coil galvanometer. So the fact that when a current carrying coil is placed in a magnetic field, it experiences a torque. That theory converts into application as galvanometer. So galvanometer is something, whenever a current flows in a circuit, it can detect that current. Okay, so that is the function of a galvanometer. Now based on this function we can convert it into particular two usable components, galvanometer and ammeter. Now this is the basic formula of deflection in a galvanometer. This is the angle of deflection in case of a galvanometer. Suppose initially the galvanometer was here and it deflected by some angle. So this angle is called angle of deflection of the galvanometer. Generally you are measuring this angle here, so say 2 degree, 4 degree, okay, 6 degree, like that. So this is the angle of deflection, and G is called the galvanometer constant, which is given by NAB by K. N is obviously total number of turns, A is the area of the coil of the galvanometer that is used, B is the external magnetic field, and K is some constant, spring constant. For whatever spring you are using with the galvanometer, there is a spring used to stop this motion. Okay, otherwise small current will give you a full deflection. Even a small current will give you a complete deflection, so you will not be able to understand how much current is passed. Okay, so because of that we have to use some restriction. There is a spring, you can see over here. This spring controls how much deflection will happen based on the external current which is passing. Okay, so if more current, more deflection, that means the force acting or torque acting on this galvanometer is more. Torque acting is more means more deflection, right? So this is the spring constant. So you remember this formula. It is of recently there are few questions which is coming based on this formula, so you have to remember it, NAB by K. Previously you could have skipped it, but last year there was one question based on this formula, so that's why I am including it. The torque acting on a magnetic dipole placed in an uniform magnetic field is 0 when the angle between the dipole axis and the magnetic field is. So torque acting is 0. Torque is what? Torque is, this is not work done, okay, this is torque. What is the formula for torque? Torque is M cross B, right? Or torque magnitude wise MB sin theta. So if torque is 0, MB cannot be 0 always, so sin theta has to be 0. So sin theta 0 means what? Theta must be equals to 0 degree. Okay, so theta must be equals to 0 degree, not 90. Not always 0 means 90. So there is a tendency that student think if it is 0, that means angle is 90. Not always. Okay. Now galvanometer to ammeter conversion. Galvanometer to ammeter conversion. So this is a diagram for this. Let us discuss briefly. An ideal ammeter should have 0 resistance. In practical ammeters, the resistance is kept as low as possible. Ideal ammeter means which is obviously not possible. Ideal ammeter should have a 0 resistance, but in practical it is not possible to create 0 resistance. Even the very costly material will still have some resistance. Okay, to convert a galvanometer into an ammeter, we need to connect a shunt. Shunt means small value resistance in parallel to the galvanometer. Okay, so if you connect a small value resistance in parallel to the galvanometer, then that is called a shunt. If you apply a shunt, then this can be converted into a ammeter. Now if you see, this Rg is the internal resistance of the galvanometer, that you cannot ignore. Okay, so we know that if you combine two resistances in parallel, their combined resistance decreases, right? So if you combine this galvanometer with some external parallel resistance, small value resistance, the combination will have even smaller resistance than this, right? Two parallel combination of resistances will have smaller than the smallest resistance, right? So to decrease the resistance, we always have to connect a very small value resistance in parallel. Okay, to convert a galvanometer into an ammeter, we need to connect a shunt, a small value resistance in parallel to the galvanometer. The current sensitivity of the galvanometer is given by phi by I equals to NAB by K. What is the meaning of current sensitivity? Current sensitivity means even a small change in the current, if it can detect or not. Okay, so the current sensitivity in high value current it can detect. Okay, so suppose 2 ampere, 3 ampere it can detect, but can it be will it be able to detect 2.1? So that is how the sensitivity depends. Sensitivity means even small change in current, if the galvanometer can detect, then that is called current sensitivity. And current sensitivity, as you can see, is basically directly proportional to number of turns, area of the coil, magnetic field and the spring constant. So smaller the spring constant, higher is the sensitivity. Higher the number of turns, higher the sensitivity. If area is more, then sensitivity is high. If B is more, sensitivity is high. Now out of all of these, area you cannot make too big. That means an ammeter will be very big in size, which we don't want. We want to have a small laboratory size ammeters which can detect current, right? So area cannot be increased up to beyond certain limit. Now if you decrease the value of K, then even very small amount of current can go through this and can damage the galvanometer. So K value cannot be decreased beyond certain limit. So only way to increase sensitivity is increasing the number of turns and using stronger magnet. So if you use stronger magnet, then sensitivity can be increased. Now galvanometer to voltmeter. Now galvanometer, an ideal galvanometer should have infinite resistance. Okay, in practical galvanometers, the resistance is kept as high as possible. It is galvanometer, not ammeter. Practical voltmeter. Volt. Okay, voltmeter. Okay, in practical voltmeter, the resistance is kept as high as possible. To convert a galvanometer into a voltmeter, we need to connect a high value resistance in series to the galvanometer. Now voltage sensitivity is again same thing. Small change in voltage, will it be able to measure or not? That is dependent or measured using voltage sensitivity, which is given by NAB divided by RK. Now here one thing is very interesting. Can you increase the voltage sensitivity by increasing the number of turns? Which is very interesting. Suppose initially we have only one turn. Number of turn was say 1. The resistance was R. Now if you increase the turn to say n equals to 2, number of turn increases, but resistance will also be increased, because resistance is directly proportional to the length of the wire. So if you increase the number of turns, correspondingly the resistance will also increase. So N by R is a constant. N by R is constant for a given material, right? So you cannot increase the voltage sensitivity of a voltmeter by simply increasing the number of turns, because if you increase number of turns, the resistance will increase, and because of that this ratio is constant. You cannot increase the voltage sensitivity using number of turns. You can increase current sensitivity using number of turns, but not the voltage sensitivity. Okay, you can increase the area, you can increase the magnetic field, you can decrease the spring constant, but not the number of turns. Number of turns trick is not applicable for voltmeter. A galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with a resistance of 2950 ohm in series. A full scale deflection of 30 division is obtained in the galvanometer. In order to reduce this deflection to 20 divisions, the resistance in series should be. Let's see. So here we have a galvanometer, some resistance and some external resistance. Internal resistance of the galvanometer is 50, the external resistance is 2950. What is the current passing through it? Current passing through is no current, but the voltage that is applied is 3 volt. So voltage is applied is 3 volt. So that gives it a full scale deflection. Full scale deflection means 3 volt, entire 3 volt. The galvanometer is maximum it can measure 3 volt. Okay, so first we have to find the current responsible for this. We have to find the current responsible for this, right? So what is the current here? So what is total resistance? Total resistance is external resistance plus internal resistance in series. So it will be 3000. 3000 is the resistance. Now what is the current? Current is voltage divided by resistance, that is 3 divided by 3000, which is 1 milliampere. Okay, 1 by 1000 is 1 milliampere. Milli means 10 to the power of minus 3, right? So 1 milliampere current when passes through this galvanometer, it gives a maximum deflection. So for a galvanometer, only thing that matters is the current. There is a limit of that current it can have. If the maximum limit is crossed, the galvanometer will be burned, or in case exact maximum current is passing through the galvanometer, it will give you the maximum deflection. Now for 1 milliampere current, how much deflections you are getting? You are getting 30 deflections. So 30 deflection is for 1 milliampere current. So how much current will give 20 deflection? That is the main question. So 20 deflection we will get by 20 by 30 into 1 milliampere, that is 2/3 milliampere, unitary method, right? So 2/3 milliampere current. So we have to reduce this current to 2/3 milliampere by applying a new value of resistance. Okay, now new value resistance we have added, say R. So what is the external total resistance now? R plus 50. R plus 50 is the total resistance now. So what is the current now? Current is, the voltage source is same, only the resistance is changed, so that current changed. So what is that value of the current? 2/3. Now do the cross multiplication, we get 9 equals to 2R plus 100. This is milliampere, sorry, one more thing. It will be milliampere, that means 3000. Okay, so it will be milliampere, not simple ampere. So you have to divide it by 1000. So from there we get 9000 equals to 2R plus 100. So 2R equals to 8900, right? This 100 will come to this side and minus, so R value will be 4450. So the new resistance should be 4450 ohm. Option C in this particular question is the correct answer. Try to practice some more questions on this. Okay, here are the homework questions for your practice. Pause the video if you want and mention the answer in the comment section of this video. And if you want to download the PDF of this lecture, then definitely join our WhatsApp channel. The link of the WhatsApp channel is given in the description of this video. Now this is the second homework question. Again, try to solve it. Easy question. I already gave you a lot of hints about this question. Answer it and mention the answer in the comment section of this video. And I will be back with a new, not new chapter, but the KCET PYQs of this chapter very soon. Till then, bye.